In this video, we're going to take a look at something I made. This is a DIY power bank to charge a Onewheel XR, a Onewheel Pint, or almost any production electric skateboard without the need of an outlet. Let's go. So around March of 2020, the entire landscape of charging your board, whatever that board may be, outside of your home became very different. Things started shutting down, everyone was starting to quarantine, and no longer could you ride for a while, then stop somewhere like a coffee shop or a small fast food restaurant, charge your board, have something to drink or eat, hang around for a little while, and then continue riding. Not too long after that, a lot of the external outdoor charge spots started to shut down. And the ones that were left, the ones that people used, especially in a city as dense as New York, those started going too. A lot of times everyone would bring a fast charger and then a power strip, and then they would all plug in at the same time and the circuit breaker would trip and those outlets would never get turned back on. So the amount of external outdoor charging spots since then have been declining rapidly, which is really what prompted me to actually want to put one of these power banks together. Now, this power bank is not in any way, shape, or form an original idea at all. There are a few prior setups, and there continue to be several different kinds of configurations that all are forms of a similar idea, of a battery going into some kind of an interface that then outputs power to your board, be that Onewheel, be that electric skateboard, whatever. So we're going to dive in. Expect a very long video. There are going to be chapter markers in the description, and there will also be a written build guide on my blog, which I will link to in the description below as well. So if the video doesn't cover everything, chances are that it is covered in the build guide down below. There's a full parts list in there. I'd say total parts, assuming you have all of the equipment to build this thing, total parts cost of this thing is anywhere between $250 to $275, depending where you get them, when you buy them, how much of them you have to buy. It is certainly an approachable project. I think accessibility to charging, especially in the current world climate where every external outlet is starting to shut down, at least around me, this is something important for, I hate to use this word, for the community to have more access to, which is why I decided to try building one of these in the first place. The layout of this whole thing in the world of DIY PEV building isn't really all that complicated. If you've successfully built an electric skateboard from scratch, then this would be a walk in the park. It's important to note that there are a few cells to choose from the class of high-capacity, lower-output 21700 size cells like the Samsung 50E, or the 50G, or the Molicel M50A, or the LG M50. The build of the battery pack itself is both simple and kind of frustrating. The layout is simple enough. It's a 7S4P configuration. That's 7 groups in series, with each group containing 4 cells. It's shaped like a brick, so no need for weird shapery there. The only real difficult part is the split right in the middle. The center parallel group of 4 cells has to be split in order for the pack to fold into its brick shape. What this requires is the parallel connection on top to be folded carefully, and then the parallel connection on the negative side of the cells has to be jumped across the side. You can do this with some wire. I used 16 gauge on my first prototype, Or, what I do now to save space and reduce soldering, is use long nickel strips covered in heat shrink, and with fish paper underneath it for more insulation. This is a bit of a pain, but it ends up being smoother and flatter on the side, which I think is good. Insulation is very important here. Where the pack folds, there's Kapton tape over the tops of each half, and some oversized fish paper between that where the halves meet. You don't want anything short-circuiting anywhere, but you certainly don't want any of these parts touching. This is also why the balance wire tabs are staggered around and should be very well insulated. So, if in doubt, add extra Kapton tape, fish paper, and/or electrical tape where appropriate. Safe is better than pretty. Lastly, and once again, insulation is very important. Put fish paper underneath folded balance tabs, between the cells that are connected in series, and anywhere something could damage a cell or its insulation and cause a short. Internal battery shorts are very dangerous and should be avoided with proper insulation everywhere. If you're unsure if the insulation is enough, stop and ask a battery builder. Actually, if you're unsure about anything, probably shouldn't be building a battery. Anyway, we all start somewhere, and so I'll include what I consider to be essential reading in the link below. Once again, build guide and resources are posted on my blog article. The BMS I'm using for this is a generic 7S BMS that fits nicely across the face of the pack. There's nothing different about how this BMS is wired, but always make sure that you have and understand the wiring schematic of whatever BMS you're using. This one has overcharge protection and a cell balancing function, and so far I haven't had any failures. But, as with all electronics, nothing is perfect, so make sure your builds are safe so that if a BMS fails, you're not at any heightened risk. For this, I use a fuse in the charging circuit rated to either 7.5 or 10 amps depending on your expected charge rate. So before we wrap this pack in fiber tape and PVC and the final wrappings, we are going to charge it, and that will run power through the BMS into each of the cells, give it a chance to balance, and also test the charging of this pack. I charge most things with either of these two bench power supplies. This one is the one I use the most. We are connecting this to the battery pack's positive and the charge negative, which is what goes through the BMS to charge. But before we even begin to wrap this up and call this done, we are going to do a charging test to full. If any of the cells get very warm when it's charging, that's bad. Any of this stuff starts to fail when it is charging, that is bad. If that's the case, do not use the pack. You'll have to very, very carefully break it back down and test each individual group and make sure that they are connected properly and that nothing has gone wrong. This thing should charge normally, and the only real group to ever be concerned about is this one on the right that's stretched across these two, considering you've got the negatives connected here in the middle and the positives jumped across those two, right? But as long as you've got those welded properly and nothing is broken when you folded the pack into the brick shape, you should be fine. As long as you've also then insulated everything as you've gone over the balance lines. So wherever these lines, wherever these cables, wherever these wires are touching, crossing, laying on top of one another, there's some Kapton tape between them, and they are generally decently insulated. Got fish paper underneath those where it's crossing over here, and fish paper wherever any sort of positive and negative cross. So, charge test. I use Kapton tape to secure the BMS onto the fish paper and then cover that over once all the wiring is done. 2 crossing layers of PVC heat shrink and the battery is complete. Again, insulation is important both around the pack and the terminal wires. Anyway, this is the interface that pulls current from the battery and feeds it to the output. It's a good idea to test it as much as possible before assembling everything and checking to make sure that it works as you want it to. So as we're testing this setup on an electronic load, we are syncing 5 amps at 63 volts from the battery through the converter, and it's just pulling it right in there. To set this, the voltage potentiometer is there, and you screw it in to increase it, screw it out to decrease it, and the same thing goes for the current control potentiometer right there. Now there are a couple ways to set that. I actually set it using the electronic load. It is not the best way to do it, but it is a way to do it. So I set this to 5 amps, start it on up, make sure that the voltage is correct as per what I need, and I screw this all the way out until the voltage drops. So actually, you can kind of do that right here, and as you decrease the cap on the current, the voltage drops. Because if you cannot provide enough current, that's what happens. So then you just increase it slowly until you get back up to the voltage that it is set to. Now, if you want to get a bit closer, because these are multi-turn, relatively slow reacting potentiometers, you can then just back it out a little bit just to make sure that you haven't overshot the current limit, and as long as it's sitting at the proper voltage, it should be fine. Now, it's not the exact way to do it. Another way to do it is to hook it up. You'll unscrew it all the way out, drop the current limit all the way, and hook it up via the output to a board, and then plug it in and let it start charging it. It won't actually send much current, and in doing so, you can hook up something like this. These are available on Amazon for very, very cheap, with a wiring diagram / schematic on the back. Those are voltage and amperage meters, so you just connect this shunt resistor in series. So, if you have an output there, you would just put this in line with it, and then it would read the voltage and the amperage that is being passed through that shunt resistor, and then you would simply increase it as the board is drawing charge until you hit the desired current. That's probably the more accurate way to do it, but I don't have this wired up, and I use this. It has worked fine for the 2 that I've built, and that's what I'm doing for this. So this has been running for about an hour or so, just a bit under an hour, and the battery is not quite empty yet. I think it's at about 23 volts. So almost at a full charge's worth of use right here. The heatsink on the converter is very, very warm. Not hot. You can still hold it. The inductor is hot. Yes, that is hot. But the heatsink, which is what really matters, is very, very warm. The case has warmed up, especially right underneath, which is exactly what we want. That means that it's bonded well with the thermal glue, and as you move around the case, you can feel the entire case is warm. Warmest underneath the heatsink, but it is radiating well out to the rest of the case, which is exactly what you want. You want the case to be sinking the heat away from the heatsink of the converter, and that way nothing actually heats up too much, but the whole thing just sort of gets warm really about 2/3 of the way into a full charge. Once it's been running for about 40-ish minutes, the case will get warm. This is not hot. You could hold it from here. And this is all very warm. And so by the time about an hour or so has run out, maybe about an hour and 10, and you've gone from 0% to 100% charge on whatever it is that you're charging, this is still just going to be warm. And honestly, once you turn it off, it cools off pretty quickly. A couple minutes and it's almost not warm anymore. So this is good. this has worked. This is still running. So I'm going to run it until this thing is just dry, battery's dry, and let it settle and then charge it back up. The case I use to enclose the whole thing is actually an amplifier case made by Hammond. This is, as far as I can tell, the same case that Chai Battery uses for their board bank, and that's the main inspiration for me using it. It's a very clever choice and it fits everything very nicely. It also serves as a heatsink when the boost converter heats up during use. When laying out the front panel, I was faced with a specific problem. I don't have a milling machine, so I was stuck with circular cutting shapes. This wasn't an issue when choosing the switch and charge port, but it was when choosing the capacity indicator. Fortunately, I found one that is not only round, but I think looks pretty slick. Using a step bit and a 3D printed holding jig that I quickly drew up in Fusion 360, making the holes for everything wasn't too bad of an issue. Putting everything together is a bit of a process, as you can imagine. What I like to do is use the battery pack as a spacing guide for where the converter is going to sit, and then use the front panel wiring to guide the centering so nothing interferes with the wires. The battery discharges directly to the converter, not through the BMS. The BMS is wired for charging only. So the discharge wires go to the converter, with the negative wire going through the main switch. This is the physical cutoff that turns it all off whenever you need to. I like having a physical circuit breaker right here. The charge port is wired into the charge circuit, independent of the main switch. I can charge the battery without the main switch being on. As I mentioned before, the charge circuit has a fuse in case anything fails in the BMS. The capacity meter is also wired independently of the main switch, since it has its own power button, and I can check the battery level without turning the main circuit on. Wiring things independent of the main switch is pretty easy here, since the input has 2 terminals each. So I put the main battery wires in one screw terminal and use the other screw terminals for all the other wires. The converter itself is adhered into the case with thermal glue. This aids in securing it and transferring heat to the case from the heatsink. Now, as you're wiring this up and you're setting up the output cable, using this 2-wire cable that I've got, you want to wire it so that it is essentially the same wiring as any XR or Onewheel charger. So this has the positive going into pins 2 and 3, which are labeled both on the front and on the rear of the XLR cable, and the negative going into pin 1. Now, something to realize is that on the stock XR charger, pins 2 and 3 are bridged, so that's why you get the positive going into 2 and 3, and the negative is just on pin 1. So these cables have the 2 internal wires, and then you just bridge them, you just jump them with a piece of wire. That's just 20 gauge silicone wire going from pin 2 to 3. Now, this cable that I'm using doesn't actually have a red and a black, it has a light brown and a light blue, but anything that resembles red I tend to use as the positive wire anyway, so that light brown wire is the positive, and the bluish is the negative. So once you wire that up to the converter right there, then just keep in mind which end goes where. If you are wiring this up for a Pint, they are actually wired pretty much like every other charge cable, in so that they have positive on pin 1, negative on pin 2. So if you're wiring this up for the Pint, then you want to be sure of the polarity. Really, you can just use a multimeter and check the polarity. Make sure that you're checking polarity of your output as you hook it up before you really secure everything down and close it up. So once this is all, well, this is finished being soldered, so I'm just gonna do some conformal coating and then screw it all back together. All right, last thing, certainly the last thing, is that once this thing is charged and everything is good and you are certain everything works, make sure that everything inside here is sufficiently insulated. So on the terminals for the converter, I put silicone on the input and the output terminals. It's just this clear silicone 2. It's neutral cure, and that's what you need. You can also use this. I think I've shown this in a previous clip, but this is also very good. It's a bit more expensive, but if you'd rather go with something that's labeled for electronic use, fine. And that's what goes there. The front panel, the ports and the meter are, well, they're screwed in, but they're also held in after that with hot glue. No heat really reaches this. This panel never has gotten warm, no matter how long I've run this, so I'm not concerned with that. And there's shrink wrap tubing all over the wires, all the solder joints, the charge port is fused, and everything is insulated and covered. And once it's all together, it's fairly snug. Not too snug, it's not crimping into one another, nothing's being crushed, and you gotta make sure to space it so it doesn't do that. But the one remaining thing is the main switch, and you can either hot glue this, you can flow some of the silicone on it, you can just wrap it with electrical tape, you can just put shrink tubing on it before you solder it and clear it from the heat, even though this is a fairly large thing to solder, so the heat will transfer down the wire. But if you can manage heat shrink tubing, that's fine too. However you want to do it, just make sure that everything in here is insulated and nothing is bare. Not that anything would move. Once this is closed together, it sort of just sits like that. Assuming you've done decent cable management and the spacing is fine, it will just sit. But make sure that everything is insulated before you close it up. Once that's done, put it all together, make sure that no wires are being pinched as you assemble it, and check that very carefully, and you should be good to go. I hope you enjoyed the video. I hope you enjoyed the build. I hope it was at least a little bit helpful. If you end up not building one of these things for yourself, I do hope it at least gave you a bit of a look into how something like this can be built. Once again, there are always options. There are different configurations to look into, to put together, and really it's just a matter of taking a similar structure and configuring it into a way that works for you. Also, mildly unrelated, the hoodie that I'm wearing is the pandemic hoodie from Bustin' Boards. I just thought it was a bit fitting because the whole spark of why I wanted to build one of these power banks had to do with the pandemic shutting down the outdoor charging spots. It's actually a very nice hoodie. This is not a sponsored video by them. I just really like the hoodie. It's thick. I've fallen in this a couple of times and it actually does pretty well. Still wear pads, by the way. But I'm a big fan of Bustin' Boards, and the DIY electric skateboard I built is based on the Bustin' Sportster deck. I have a Bustin' Bonsai Mini Cruiser, which is a lot of fun and kind of just fits everywhere, and so big fan of their stuff. And this is a very nice hoodie with a wonderful hood, very robust thing. So I do hope you enjoyed the video. If you haven't already, please do subscribe. Once again, check the build guide in the link below on my blog. It'll have detailed photographs, parts lists, stuff like that. If you want to attempt to build one of these power banks yourself, make sure that you are keeping yourself and everyone around you safe. Don't want to start a fire. It can get very bad. Now, I built a few of these for friends. I'm going to build a few more for a few of the local riders around New York City because, like I said, not a lot of outlets around these parts. So stay safe, don't fall.